Alright, hello everybody. Welcome to the last 4-coder stream of the year. By 4-coder stream I mean I'm testing out a new 4-coder as I work on some test project. And the test project I've been working on recently is the wave function collapse generative algorithm thing you do. So that's what I'm working on. And let's just pull that up real quick. Last time I had gotten rotation and flipping working, but rotation only works if you have a square window. And there's also the issue that the rectangular windows only allow rectangles all going the same way. So let me draw a picture of this because it's a little hard to describe what's in my head with just words here. There we go. So the main problem is that I've got this set of samples, right? And if they're all squares, it's great because they're all the same shape, right? That's a 3x3 there, and then if I rotate that, I get 3x3s and everything. But if I have rectangles, right? If this is 2x3, for instance, then I also kind of want to be able to support at least 3x2s, right? I want to be able to support rectangles of this kind. And the reason for that is having both of these simultaneously lets me do fully get all of the features that are 2x3 of both rotations, which is nice for like the automatic tile generator type functionality that the original thing has. So right now what I was looking at the end of last time was figuring out how to support at least 2 different tile sizes simultaneously, and the problem is that the way it's organized, I have these sample sets, but the samples themselves don't know their sizes. The samples are just some data, and there's a bunch of them, like this, do, and it makes up a big sample set. Maybe a little dot here to demonstrate that there are a lot of them. And then you have the sample set that has a little bit of extra data here that says, oh, these are 2x3, right? So it knows how big they are and how to get to the one it wants and all that stuff. So you can say, alright, here's my sample set, here's my information about the size of the sample, I can get that easily, and then I can go to any sample in that sample set. But if I have a new sample size of 3x2, the rules for how those samples need to line up with each other are a little different, and I'm debating whether or not to try to allow that. Now, the thing is, the original thing didn't actually do this generally. If you actually look at what it did, it looks to me like they implemented a special rule for propagation that didn't rely on sample overlap at all, and actually their sample system does rely on square samples. So what I think I want to do, now that I think about that, is I think I want to skip this. I want to go ahead and say, let's for now skip the sampling, the tiling thing, because that's sort of a different thing that, you know, the way they implemented is separate anyway, and maybe someday I'll generalize to that, but I'd really like to, since it's the last stream of the year, I'd like to get to what I originally wanted to do with this project, which was to start to optimize this thing. So I'm going to say, let's gut the tile stuff and just focus on the other aspect of this. And you know, as I think about it, I bet there's a way to cheat on the tile thing anyway. It wouldn't be pretty, but it would be possible. Well, I'll save that line of thinking for later. Yeah, I want to go ahead and not deal with trying to support 2 different tile, like rotated tile sizes at the same time, and say let's go back to just using squares for now. And let's see, I started to generalize last time the samples array. let's see. End samples. Get debug output. Generate output. Yeah, so I'm going to actually leave this in the state it's in, I think, maybe? What should I do? Samples. What I just did was to generalize this procedure to multiple sample arrays. And yeah, I don't want to actually do that because I remember, okay, so I've been thinking about it, and it kind of deeply complicates the amount of work you have to do here because to sample, like each cell needs one coefficient for each sample, even if those samples are in separate arrays. So then what you have to have is a way to like map an index that is larger than the first sample array into the second sample array and then pull it out in sort of this double indirection thing with a little bit of shifting arithmetic and stuff. I just don't like it. So I'm going to leave it the way it was with just supporting one sample, and I'm going to roll back some of the API that makes it seem like it can do more than one sample. Samples. And that's going to break a few things, but that's fine. We'll just fix those. So sample array count is no longer a thing. And hey, why is this file... What's going on here? The wrap position on this file is definitely not using the new rule. So let me look at something here. That's 4013. Yeah, that's what it's supposed to look like. Not sure what just went wrong. Well, anyway. Oh, you know what that might have been? Oh, I bet I know what that was. Okay. Maybe it was this. I'm not sure. Actually, I have no idea what that was. Ran the wrong version or something. Oh, there it is right there. Look at that. Oh, is that because... Aha. There's a forecoder bug I just found. So, that took the total width. What I want is more like the average width. Why did I take the total width divided by... The total width divided by 3 should have been different, though. Okay, 1 minute. I want to go track that forecoder bug down. So let's take a look. That was in the... ViewAdjust. I added a new hook that lets you know whenever a view size has changed so that you can automatically adjust the buffer sizes to it. But what's going on here is a bit weird. So I take each file region. I should be getting... I should be getting 3 widths that are all the same, dividing by 3 and getting that original value, but somehow it became much smaller. I'm going to need to... Alright, I'm going to need to switch projects and go debug this properly. My ViewAdjust, where is that? Way up here. Okay, so that's correct. In fact, if I do that, it'll be exactly like it was before, but there's no breakpoint showing up right there. Huh. Alright, hold on. There we go. So I want to go there. So what I'm doing here is just trying to figure out why the wrap width changes, because it shouldn't change when I build, but it does. So let me see, I build. We come in here. Now, what happens? We get the first view. Which view is this? View ID 14. And it has a width of 0. Wild. Okay, 1 minute. So that explains it. If it thinks there's a width of 0 on that view, what I want to see is layout, panels, 16. So this here has a non-zero width, that there has a non-zero width, but this one shouldn't have a non-zero width, but it came out as 0 in the other spot. Huh. So this comes through here. View ID 14, index 13. Alright, so I need to see this again from the top. Not now. But after I do this. Getting the first view, what does it do? Comes in, it gets a null view. I should change that code there. Get view, internal get view first. What happens there? It comes in, says here's the sentinel, get me the next panel. That panel, fill view summary. That panel has a view, right? That view has a panel. Fill view summary. That right there, vputter file region. Oh, I see. That's nonsense. What is that file region even used for, I wonder? Okay, well I don't care. I want to replace that with the panel. Do I have input from the vputter panel here? Okay, let me go to line 90 of API implementation. That should be panel inner. Okay. Okay, so we pop in here, and now what we get is comes in here to get the first, and when it goes to fill the summary, the file region comes out non-zero because it's grabbing it straight from the panel instead of from the file. And it looks like that worked. So I just need to package it again so I can use the fixed version for the rest of the stream. There we go. Alright, switching back to the wave function collapse project. And there we go. Perfect. Okay. So that was just a bug, and I got some legacy crap that I'm going to start cleaning up in the next few months as I just do some housekeeping in the 4-coder code base so that that crap doesn't happen anymore when I try to add new features. I have a lot of places where there are things that I wanted to see whenever something changed. Like I wanted to see whenever that changes, I want to do something later. And rather than keeping a dirty flag, which I've decided is probably what I ought to do in for things like that in the future, I would keep multiple copies. I'd keep the sort of at the beginning of the frame, here was the value, and then at the end you check and see, is it different? If it's different, then you assume a change has happened. Well, the problem with that is then you get into nasty things where, okay, well, what if another thing wants to propagate? Like, that ends up with sort of this thing of you have this value it's ambiguous, like when certain events happen, and it sounds like starting with the previous value and then checking at the end sounds like a nice safe way to make it work, but in practice nasty stuff like that happens all the time where, well, you end up relying on the previous value laid elsewhere in the code, or the sort of propagated version of it, even though it's like one frame off, like it's one frame old. And the reason you rely on it is because it's not in like a half-edited state or something, and so you treat it as more correct, and then you end up with several layers of propagation, and you've made a new panel, but some of the things related to that panel say that the panel has a rectangle of size 0, whereas other things say differently, and so you got nastiness everywhere, and it's unclear who's authoritative about what the actual size is, and then so you write code that uses the bad one that's got slower propagation because it has some other property you think is important, and it's just a mess. So my goal is to clean up a lot of that crap in the next few builds over December and January, so that I don't stop having like stupid bugs like that all the time. Alright, so the idea now is that we have one sample set of samples like that. Samples sample count. Alright, there we go. So now we're down to using square windows and let's see, I want to do processing params. I want to do rotation level is the second to last one. I want to do 2 rotation levels and one and enable mirroring. Once you're doing 2 rotations, I guess once you're doing any rotations, it doesn't matter which type of mirroring you enable, but you still need to enable mirroring so that you get the other. I'll explain it some other time. Basically, there's 8 orientations that you can get on a square that's on a grid, right? 4 rotations and a flip 4 rotations. Doesn't matter what order you do rotations and flips in. Once you've got all 8 of them, there's no other way to there's no other things to get to. That's the idea. Okay. Anyway, so now we've got the rotations and everything, and I want to start trying to speed it up. So first things first, I need to see how slow it is, and I'm going to run it myself and just sort of get a feel. Okay, that's not very slow when it's a 3x3 block. The 3x4 block or whatever it was slowing it down a lot more, I think. But yeah, that is pretty neat. Look at that. It's still got that pattern there, which is so fascinating that it recreated that. Okay, and now what I'd like to do is set up a timing situation so we can start to get an idea of how quick that is. So debugging. Let me list all the locations where I see debugging so I can see the different debug levels I've got. Debug level 0, 1, 2, and 3. Alright. Debug level 4. Timing. If defined debugging and debugging equals 4, and if a little bit dark and creepy now. Let me lighten things up again. There we go. And let's see. We need the timing stuff. So how do I normally do timing? RDTSC. Let me actually pull up a quick browser window here. RDTSC. Is that how I want to do it today? Might as well. In train.h. So basically, what I want to be able to do is just do begin time, end time blocks, and it looks like what I need for that is a uint64t. Well, we could go a step simpler than that, which is begin time. Define end time, and then I'm going to do basically the idea here is begin time will just return, not really return, but it'll give the an unsigned 64-bit integer that you pass in here. So here's your S value and your message, and then you do something like uint64t total equals RDTSC minus S printf %s colon % long u maybe mt new line, and this right here is like I think I want to put like a 10 there if I'm remembering correctly how it works. And then here I'll just do 0 and do nothing. Alright, so let's try this out. I want to first, let's see, this here, get processed samples from scratch. Begin samples. Yeah, let's begin time. was that right there? Okay, what I would like to do is tell this thing here, if print result if defined debugging and debugging equals 4, print result equals 0. So getting the samples doesn't appear to take much time at all. I say that just because it appears so quickly. And let's go ahead and wrap that all the way around all of this. And I have to keep it like that. Okay, and then let's see, we need another one right here. Get samples time, get generation time. Output width 30. Output height 30. 30 times 30. One other thing, these should all be capitalized so that it looks like they are properly macros. Alright, so next up, it's not padding this the way I want it to. So let me just find that real quick. How do you make this thing pad it properly? Let's try increasing the size first. Okay. Let's try that way. Now it's padding it with zeros and still not doing what I want. That's not so bad. I could deal with that. I'd still like for it to align the numbers so that their digits line up correctly. Perfect. There we go. Alright. So, a gigantic amount of time is spent on the runtime, which is good. That's where you would expect to see it. Which means now we want to break down that. Let's see. Generate output. So here I need something more clever. Begin time, define begin, time counter, Alright, so that gives me a time counter which I can use to accrue when, because basically what I'm going to have is events of type A and events of type B, and they're going to go back and forth for a while, and I want to count how much time do I spend on events of type A, how much time do I spend on events of type B, and I might even break those down into like a type A is made up of A1, A2, A3, and I want to count how much time I spend on each one, and in order to do that I need to be able to create these counters, and then well, this should be like make time counter actually, and actually what I should do is just put in a null time counter there, and then say null time counter equals blah. Actually, that can go here. We'll just always have that available. That will always be, whoops, that will always be how you make a time counter. Then, if I want to begin time counter, I pass in the counter, and I just say, okay, counter dot, or I should say counter arrow start equals RDTSC. And time counter C will read C total plus equals RDTSC minus C start. And those will just do nothing when I'm not running counters. Okay. That way I've got the ability to make one of these time counters and then start and stop it multiple times and add up the total amount of time it's spent. Let me come down here to output, generate output, if defined debugging. So if we're in debugging mode, I don't want to always have this thing spamming the world with these empty counters that don't do anything. But if we're in debug mode, I can, and since all of the interactions I do with them are through those macros anyway, these will just get ignored. The missing variables will just get ignored when debugging is not set for timing. Okay, so I want to be able to time the amount of time I spend on an observation and the amount of time I spend propagating. First of all, that's the first thing I want to do. So time counter observation, make time counter, and propagate, make time counter. Right? And then all I have to do is right here, where do I begin propagating? Or where do I begin observing? I begin observing right here, so begin time counter observation, get all the way down here, and end time counter for observation, and begin a time counter for propagation. Propagate. Propagation. Propagation. And then end the time counter for, let's see, where does propagation end? Change count equals 0. Alright, so here, different debugging things happen. There is the actual end of propagation. Okay, and then when that whole thing is done, if debugging set to 4, then what I'll do is display time counter C um, that will be the same as end time message c.total and £c. Debugging equals 4. Display time counter. Observation. Propagation. Display. And that should be C arrow. Observation. Observation took a lot more time than propagation. Interesting. I did not expect that. Well, then I should break down observation and see what else goes on during observation. Does that hold up over multiple runs? I assume it must, right? Oh wait, no, that was different. That time, propagation took all the time? Okay, this doesn't even make sense. It can't be true that the total amount of time spent observing plus the total amount of time spent propagating can't be greater than the total amount of time spent generating. That doesn't add up at all. Yeah, that happened here too, actually. That should be 37, that's only 32. Here it looked like it was correct, but that's confusing. So what's going wrong there? Begin time counter. I begin observation, I end observation, I begin propagation, and I end propagation. So they both get begun and end same number of times, and they don't have any overlapping time at all. What? Yeah, this here cannot be smaller than that. Runtime Generator runtime. Telling me the totals that I got there and there were larger than... That doesn't make any sense. That's not like inside of a loop or anything. Nope. I mean, like, not a loop that's separate from this, so it happens the same number of times. Well, what's all this? What? Okay, there it goes. That's weird. I have no idea what that was all about. Because I had ZI specified twice that it was confused? I don't know. Anyways, what I want to see is observation started there and it has a total of 0. If I run all the way down to here, obviously it's going to blow the time up now. But it's still got a total that was reasonable. And this here, we begin counting, we get a start, we get a total. Observation, propagation. So it spent some time in both of those, and it's fine, it's whatever. So how are things going right here? Generator runtime. Yeah, so that did start sooner. It should end up later. Observation goes up a little bit. Propagation goes up a little bit. Oh, it's going to go up a lot, but that's okay. Up. Eventually we're going to end up here. Up, boom, 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 boom. Each time we go increasing one of these a little bit at a time, but there's no way that I can imagine that it should come to the conclusion that the sum of these is greater than the sum of the whole function. These are non-overlapping segments. Indentation of 2, indentation of 2, indentation of 2. Okay, so that seems reasonable because I spent a lot of time. Most of the time I spent was actually in between each section looking at the numbers change. That is unreasonable. Don't understand how it's getting stuff like that. Yeah, it doesn't make any sense. Feels like it must be double counting something or something. I don't know. Let me add in some extra stuff to sanity check here. Ah, there it is right there. I'm a dummy. I can't just pass that to end time message. That has a totally different behavior. So that'll explain it. See, what was happening was I was passing that here, and so then it was taking the total and doing RDTSC minus the total, which is completely pointless and irrelevant. Actually, what's surprising is that it didn't give me more ridiculous answers. Okay, if C start count equals C end count, then printf some good stuff, %30s, %20 lu, message C total, message printf, all that stuff. Put in a new line and then percent, let's see, the word average. Well, let's do a %30s on an empty string. Oh wait, on the word average. %20 LU, new line. %20 LU, and these should have like an extra 5 to indicate that they're special. So that's M average, and you get the average by total divided by start count, which we know is equal to the end count. And then finally, mem count, which we get right there. Oops. Then we can throw in a little else. Printf %30s error count mismatch error, new line, %LU, %LU, which is message. Huh, fascinating that I made that work. Look at that. So cool. Message times, not message times, message and then message and then start count and then end count. There we go. Alright, so what this does right here is it either prints out all the results. Guess I don't actually want these on separate lines now. Or it displays an error, right? And then I can just throw in an extra display time counter, put in a C, and that's just display time counter message, C, string C, throw in an M there. Display time counter message, build. What do we get? Uh-oh. So a couple things. If this increases by 4, these ought to decrease by 4. And tell me observation has a mismatch in its count. Oh, because I break out of observation at the end and don't count that last step. Right. So observation, go to finished. This is the one where I'm not failing, right? So right there I want to end time counter observation, and there we go. Alright, so now I can see I'm hitting observation 127 times, propagations 126 times, and let's see, the total amount of time I spend in observation is, looks like a lot less than propagation. Now here's a question for myself. Do I want to show these extra average and count details or not? How do I want to show them? There we go. So the average and the counts go over here so they don't line up in my nice columns here and confuse me. So here I've got an average of that with 127 of those give me that, and then here's the average for one propagation step, which confirms my original theory that propagation would actually be more expensive. Alright, so we just spent the first hour of the stream. I'll probably go long since this is the last stream of the year, but I just spent the first hour debugging the timer setup so that I can actually start to optimize stuff. But what we have so far is I can see the propagation. I can see the propagation is taking up the most time, and it's sort of very consistently showing up right here at around this range of size. And this here, sorry I'm speaking slowly, I'm reading some of these numbers and comparing them to make sure I like it. Yeah, okay. This one is about consistently 1/30th of this. So the most time I can save is actually in this propagation step, which is what I was expecting. So now that we know that, let's do you know what I could do? Okay, I know how to fit this stuff in a way that will look good. Let's decrease each of these by 10, because I don't really need this much space. That isn't different at all. Ah, right. I need to pull up the other ones, these ones right here, and decrease these as well. There we go. Yeah, it's just barely enough room, but hopefully that will work for everything. And then what I want to do is I want to take the numbers and move them a little closer. So let's make this more like 12 digits of space. So 2012, 2012. Alright, very good. Now let's take these right here. Let's simplify them. Oops. And so that changed there. Let's me say hold on, this is gonna bug me the way I set this up. Yeah, I really need to make the sort of automatic macro handling system. Maybe that'll be my first thing once I'm done cleaning up the current stuff that I have. Okay, so I've got those shifted over. Now I want to move these I've made them smaller and I want to move them over farther to the right. So this has a total of 20, 21, 22, 32, 34, right? So I don't want these ending at 34. I want to give them a little more room over so that they don't overlap at all. So let's make these like something like 44. And then let's make these nice and small, since they're not that big anyway, like 10 and 10. There we go. So now I've got averages and counts for these complicated things like observation and propagation, sort of off on a separate column, and then the observation and propagation things line up nicely by themselves there. I like that quite a bit. And now let's see. I want to break propagation down into more details. So, let's break propagation down into how many changes do we do per step, basically. So, single change, that's what I'll call it. Propagation, begin time counter for a single change. Oops, single change, end the time counter, and then to display it, single change. So a total of 8,000 single changes happen. Each single change has an average of 387 cycles each. Now that's a little tough because we can't change this count directly. I don't think. I can't think of a way to change the count without drastically altering the algorithm. Or not drastically, but even subtly, right? I want to not change the rules of the algorithm, just speed it up, and I don't think there's any way I can decrease that count, because that's kind of just a product of the rules, if I am remembering correctly. I don't think there's anything you could do there that would be smart. I mean, what can happen is you make a change in one spot, then you propagate that to its neighbor. That neighbor then goes, oh, I need to change, and then it propagates back to yourself. And if you, aren't careful, what might happen is every time you propagate back to that self, like if I make a change in one spot, and then I have to change all the neighbors, and then I run all those, and then each one of those 8 neighbors then says, oh, that guy in the middle, he's got to change it, and he ends up in the change queue 8 times. But I'm pretty sure there's actually a safeguard against that says if something is already queued up in the change queue, it has a bit that gets set that says, hey, I'm already in the change queue, don't worry about me. And so that means it eventually will get processed again. Now, the order in which propagation happens, it seems to me, is kind of irrelevant, because it's not like if propagation happens in this order, you should get a different result than that. Either way, you should end up with the same result. So maybe there's a way to reduce the count by picking a count that reduces the amount of times you track back. I'm not sure. I mean, I wouldn't think you need to track back more times than the radius. So like if I have 3, that means the center around the area that gets initially changed is 2, right? Because my window is 3, which means if I'm right here, then there's 2 other guys who get affected by my change in this direction, and 2 in that direction. And so the total number of times you probably have to have stuff tracked back to you shouldn't be more than, well, make all those changes. I guess if you propagate far enough out, you hit a boundary, and then stuff propagates back to you from that boundary. It could happen an arbitrary amount of times. Because once you have two things that are partially filled in here and partially filled in here, and then you sort of make a change here, well, that change then propagates from this edge over here, and it has to go like, oh, well, this change is going to connect these, and oh, that's going to have to propagate its neighbor into its neighbor, and then, oh, this thing here says that this thing can't be that, so propagate back that, oh, it can't be this thing, so it's got to be one of those, and it bouncing back and forth is kind of this like, oh, it can't be one of these, and slowly eliminating possibilities until the only possibilities left are feasible ones. And it can't learn if something's feasible or not until it's propagated out to a spot that says, no, that's not feasible. And then it has to send waves all the way back saying, this thing we thought was feasible, turns out it wasn't, and then you can eliminate more stuff, and that elimination can then teach you that even more things are infeasible, and then the wave propagates the other way again. So I think there's no easy way I can think of to just reduce that, but it shouldn't actually be fixed, actually. So I should be able to change that count without breaking the algorithm, because the number of times it happens, as long as I'm not just short, as long as I'm completing the propagation, it doesn't matter what order it happens in. Okay, so that's interesting to know. Now here's another question, which is there a lot of time? No, there's not a lot of time spent. Well, it's hard to say from this. Yeah, so definitely the most expensive step is propagation. And you either have to decrease that count or decrease the average. Now, if you decrease the count, you get better results, because if you get a lower average count, if your count is better across many inputs, then this big number gets reduced, right? On the other hand, that might just be kind of arbitrary because these have different units. So I'm not sure that I'm thinking about, well, no, because this is not really got units, it's just a count. It's the multiplier on this average here. It's probably easier to bring this number down, though. By large amounts. So that's true. Alright, let me think about this another way. Let me read through this code and see I think I'm already doing that. Just doing that right up there, right? Okay, so one thing I'm doing that's wasting time is for each cell, I keep an array of ones and zeros. So I have a big grid, and each spot on that grid is a cell, right? So here's my grid. Whoop, 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 whoop. Here's one cell. That one cell, if I zoom into it right here, it has a big array of possible samples that could be put in the corner of that cell, right? So if I put a sample right there, depending on which sample I pick, it assigns a value to this cell and to all these grid cells around it, right? So each of those samples is given a spot in this little array, and these are called the coefficients. And the reason they're called the coefficients is beyond me, because I don't know how quantum mechanics works or anything like that. But basically, initially these are all ones, saying that all of these samples are possible samples. And over time, what happens is some of these ones get replaced with zeros. So like, I'm going to turn these into x's like that when they get eliminated. So you learn, oh, that sample can't go here. Oh, that sample and this sample can't go here. And the way we learn that is that the neighbors who have some neighbor to the cell loses either gets assigned a value, or it itself also has lost some possible samples from its neighbors, that are even farther away, and so without those possibilities, we learn that there's no way for this particular sample to show up in this cell, right? And you just keep doing that. Maybe this is after one cell not too far away got assigned a value, and then it propagated to this one, and this is the result, right? And what happens is next time, in order to see, whenever it does the loop to find out, alright, which samples of this cell are still possible, it loops across all of them, even the ones that are zeroed out, and just says, alright, is this one still available? No. Okay. Is this one? And you can see that happening here in a doubly nested way. So we loop across all the possible values for cell 2 and look for the ones that are still feasible. Look all the ones of cell 1. So I have this to-do item here, which is to find, to sort of set up two arrays. One that is this, and one that contains, at the beginning, just like same number of cells, and each cell contains, well, each spot in the array contains an index into one of the samples. Now, this number of samples is large enough that you need probably at least 2, probably 4 bytes to store it in bad cases, right? So this is actually quite a big array, but let's just say we do it and the memory isn't a problem, right? Because usually that would be the case. Then we could start like this, and then after one step of propagation we would learn, well, 1 is not possible, so I would cross out this 11 and put an 11 here. Then I go 2, 3, 4, those are all possible. Oh, 5 wasn't possible, so we crossed out 5 and 10 came in here. Well, I should say cross out 10 and put it right here. Then we learned, oh, 6 isn't possible, so we crossed out the 9 and we put it right here. And then 8 isn't possible, so we cross it out and don't do anything with it, right? So now what we have is a list that goes 11, 2, 3, 4, 10, 9, 7. If I want to know the coefficients, I still have that array. The only problem with this is if I ever want to ask, like, the other way around, like, hey, look at sample 4. Ah, yeah, we have it. Okay, eliminate it. Well, oh shoot, now I gotta find sample 4 in here. It could be here, but it might have gotten moved into one of these spots, or like sample 11, right? If I go, alright, does this thing have sample 11 just out of the blue? Then eliminate it. But I don't think it ever gets eliminated anyway, except in that iteration, which means it would actually always know the location of this, and I might be able to eliminate this. I'm not sure. I'm not sure. Let me take a quick look. Where else do sample coefficients come from, or get used, right? So cell 2 comes from coefficients. Where else do coefficients come up? Cell coefficient. So right here, we're doing the same thing. We're doing an if on it in each spot. Coefficients. Anywhere else? So we initialize all of the coefficients in the entire array to 1. Where else do coefficients get used? Debugging 0. Coefficients is uint 8. I look up the cell. Alright, so this is for printing out the map. I'm basically here saying, again, this would be better if I didn't have a coefficients array, but a list of remaining possible things. Coefficients. Yeah, so I'm going to go ahead and go on a limb here and say we can go ahead and clean that up into a better system. Alright, so rather than coefficients, and what's coefficient count? I see, I see. Alright, so rather than coefficients, what I want to do is say, something like, we've got uint32, feasible states, and now that's going to create all kinds of breakage. Let's go and find the breakage. So coefficient count, no, not valid. Alright, so what we do want is here, I want feasible states, and the number of feasible states is uint32 feasible state count is grid cell count times sample count. And I also want to increase that by 1 because I want to include on this, I'm going to make it 1 longer so that I can put a count here at the very beginning telling me how many of these I actually still use. Do. Shit. So like here, these 4 are all X'd out. And we end up with 1, 2, 3, 4, 5, 6, 7 possible things. So I would have a 7 there in the count, right? So that I know how many do I have uneliminated still. So, you know, one quick thing. Let me undo all that. I'm going to do a quick using old style coefficients. I'm going to write down in my scratch that with coefficients we get can I do like you know what, let's do it this way. No! No, get out of here. What was that? You jerk. How can I do this? Echo. No, that's not what I meant to do. Dir. Build.bat. Right, so run // build / WFC. There we go. Because I want a copy of all that. Thank you. little advanced for coder. I gotta make that better though. There should just be a run and output into for coder button. Or I can make that a part of the... I know what I'll do. I know what I'll do. Yep, it's gonna be cool. Maybe I should build that stuff into 4014 actually. I feel like that would be good. It's time. It's time to do that. I just made a 4013 tutorial on running a project, but 4014 is going to get an upgrade for that. Alright, anyway, so let's go back all the way to there and continue. So, coefficient count, where is that showing up? Yes, don't need that. Next, coefficients. Don't need that, but I do need is feasible... Oh, uh-oh. Alright. Feasible state count. No. Feasible state. Right. So now what I want is grid cell count. Do I have that? No, why not? It's called cell count, that's why. Okay. Go across all the cells for each cell. Alright. I want you to go across all the samples. I is less than sample count plus plus j. Feasible state equals j plus plus feasible state. Feasible state pointer. So this is just going to be a quick little feasible state pointer. At the beginning of each one, I'm going to write a quick little sample count. I guess these could be written with a little trickiness like that if I wanted. Alright, so I look at can't count, and I put that at the beginning of the array, and then I go 0, 1, 2, 3, 4, blah, 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 all the way up to n minus 1. Then I just loop back around to the next cell and keep going, right? In that way, every single cell gets a spot, and what I should include here is the cell stride, which is going to be sample count plus 1. Then stuff like down here, I'm going to use cell stride. Now, before I go any further, I'm going to take a quick break. I will be right back to continue doing cool stuff.